Good day to the panel of judge and my fellow friends. My name is Chong Kang from University Tunku Abdul Rahman. My final year project was done under the supervision of IR Dr. Ip Kin Ho and moderated by Dr. Yu Tiong Kit. Today I'm going to present my final year project with a title Design of Planar Microwave Sugar Level Sensor using Circular Split Ring Resonator. This slide shows the table of content for my presentation today. For the introduction, it is divided into three parts, which are background, problem statement, and aims and objective. Recently, the portable planar microwave sensor has become popular in the healthcare industry, especially for the blood glucose level monitoring, as it provides a faster response time and higher accuracy than the traditional sensor. The samples of a glucose are characterized by measuring the variation in their electromagnetic property respectively. The electromagnetic property vary from sample to sample as each sample is made up of a different composition of substance, environmental temperature, and frequency. And in this project, different composition of substance are used to manipulate the changes in the electromagnetic property of the sample under test. And the reason why this research was conducted is because diabetes is a serious health problem in Malaysia that affects more than 20% of adults over the age of 30. And in years 2013, a study that looked at people from over 175 different countries discovered that more sugar in the food or drink supply would lead to an increase in the diabetes rate. The physical effects of diabetes include eye disease, cardiovascular disease, kidney disease, nerve damage, and gut infection. And besides, the mental effect of diabetes includes stress, anxiety, and depression. Next, the objective of the project is to design two cost-effective and high-accuracy planar microwave sugar level sensors using a circular split ring resonator with a coplanar waveguide in the high-frequency structure simulator. Besides, the objective of this project is to determine the concentration of sugar level in the beverage by analyzing the resonant frequency of the S21 parameter of the planar sugar level sensor. There are a total of 6 theories that will be discussed in this presentation. The split ring resonator, also known as the SSR, was first discussed in 1990 by the Pendry, Holden, Robin, and Stieber in their Magnetism from Conductors and Enhanced Nonlinear Phenomena paper. SSR is a microstructure etched on the dielectric substrate that is frequently used in the fabrication of metamaterial to achieve a negative permeability value. SR is made up of non-magnetic material such as copper, which can enhance the magnetic coupling to a value that does not exist in the natural material. The split in the ring effectively behaves as a parallel plate capacitor, hence it can be represented as an equivalent LC circuit as given below. The value of capacitance and inductance will depend on the diameter of the ring, width of the rings, and the width of the split material used, and other such parameters. And according to the Faraday's law of electromagnetic induction, when the time-varying magnetic field passes through the metallic ring, it will induce an electromotive force which producing a rotating current. 15 ohms is a special number of impedance in most of the RF and microwave-based applications, and according to the explanation given by Germo in microwave tubes, 15 ohms is chosen as it provides a best trade-off between the power handling and the insertion loss of the air dielectric coax. ANSYS HFSS is an industrial standard software for 3D EM simulation, and according to the research done by Javita and others, HFSS uses finite element method to calculate the parameters such as resonance frequency, S parameter, and field, which can design the antenna more accurate than the CST, because CST uses finite integration in technique, and therefore the ANSYS HFSS is widely used by engineers around the world to design and simulate the electronic products with the high frequency band, including antenna, RF or microwave component, and printed circuit board. And the resonance frequency for various glucose concentration from figures 2.6 was summarized in the graph 2.1, and according to the graph 2.1, it is observed that the designed sugar level sensor for F-alpha substrate present an extraordinary frequency resolution that will be useful to characterize different concentration of glucose with a relatively tiny distinction in their dielectric property. And the frequency resolution for the glucose level change at the respective resonance is 0.0035 GHz per 0.2 gram per 10 milliliter, and therefore the resonance frequency resulting from filling a specific concentration of glucose solution can be estimated using the linear regression model derived as shown in the equation 2.1. And on the contrary, the unknown concentration of glucose in the tested sample can be predicted using the inverse model. For example, with a resulting frequency of 2.03450 GHz, the unknown concentration of glucose in the test sample, which is represented as X, can be calculated as shown in the equation 2.2 and 2.3. The simple design proposed in this project allows the Planar microwave sugar level sensor to be fabricated on large scale. On the contrary, the complicated design proposed in other literature requires more time to fabricate the sugar level sensor. Furthermore, the low resonance frequency of the design sensor was used in this project, which only requires a simple pocket VNA to measure. In contrast, the high resonance frequency of the design sensor proposed in other literature requires a more professional VNA to measure. This means that the planar microwave sugar level sensor in this project can be taken to anywhere because VNA is small enough to fit in a pocket, and on the contrary, the sugar level sensor proposed in other literature are not non-portable as the size of the professional VNA is large. It is also important to note that this project planar microwave sugar level sensor has a better accuracy and sensitivity, which is in kHz per milligram per deciliter, than the sugar level sensor proposed in other literature, which are in megahertz per milligram per deciliter. For the planar microwave sugar level sensor proposed in this project, the unknown concentration of glucose in the tested sample can be predicted using the inverse linear regression model. On the other hand, the sugar level sensor in other literature cannot figure out the unknown concentration of glucose in the sample that has been tested. In other literature, it's only known that the resonance frequency of a sensor that has been made decrease as the glucose concentration rises. And there are a total of 4 phases in this project. During the mathematical analysis of the circular split-ring resonator and the coplanar waveguide, there are two important parameters that need to be calculated. One is resonance frequency and the other one is the characteristic impedance. Then, there are a total of 5 steps in the phase 2. The first step is to design the split-ring resonator, substrate, and the coplanar waveguide in the HFSS. The second step is to select the solution type. The driver model solution type was chosen for this project because it provides a S-matrix solution that are described in terms of waveguide mode, incident, and reflected power. The third step is to select a parametric model geometry of material. The implementation of the metamaterial requires an infinite repeating of the unit element in the lattice vector direction, and therefore the boundary conditions are imposed on the unit element to meet this need. The excitation pods are necessary to excite the structure once the boundary condition has been set, and the excitation pod illustrated in the figures 3.7 and 3.8 guide the incident wave to travel from the bottom to the top of the unit element. And after properly assigning the structure boundary condition and excitation, the next step is to add the analysis setup as illustrated in the figures shown, and the structure was simulated at a suitable solution frequency, 3 GHz in this case. And the last two steps in the phase 2 is to generate the result in 2D report fields. The magnitude and the phase of the S parameters were extracted after the simulation was finished and illustrated in the figures below. After the resonant frequency from the HFS simulation was matched with the mathematical calculation, the planar microwave sugar level sensor was sent for fabrication, and the fabricated sensor is as shown in the figure below. Fabrication of the circular split ring resonator was followed by soldering of the SMA for successful transmission, and the simulation results were empirically validated using the VNA, and in this project, a total of 2 sets of PCB will be measured, one of them using the FR4 substrate and the other using the Rogers substrate, as shown in the figure 3.15. The beaker is then filled with the different concentration of glucose that will be used as a sample under test. Last but not least, all the major results were recorded, and the result will be discussed in the chapter 4. And the figure 4.1 shows the simulation of characteristic impedance for FR4 substrate using HFSS. Figures 4.2 show the simulation of characteristic impedance for Rogers substrate using HFSS. The mathematical calculated characteristic impedance for FR4 substrate is illustrated in the figures 4.3, while the mathematical calculated characteristic impedance for the Rogers substrate is illustrated in the figures 4.4. It's clear from the table above that the simulated values are very close to the calculated value because the percentage error is less than 3%, and from here we can conclude that the impedance mismatch between the VNA and the sensor themselves is at its minimum. Figures 4.5 show the simulation of the resonant frequency for the FR4 substrate using HFSS, and the figure 4.6 show the simulation of resonant frequency for the Rogers substrate using HFSS. Figures 4.7 show the measurement of the resonant frequency for the FR4 substrate using a VNA, and the figures 4.8 show the measurement of the resonant frequency for the Rogers substrate using the VNA. The mathematical calculated resonant frequency of the design sensor using FR4 substrate is 2.258 GHz illustrated in the figures 4.9, while the mathematical calculated resonant frequency of the design sensor using Rogers substrate is 1.619 GHz illustrated in the figures 4.10, and based on the calculated percentage error in the table 4.2, there's a good agreement between the calculated data and the HFSS simulation data. And based on the calculated percentage error in table 4.3, there's a small difference between the calculated data and the actual PCB measurement data due to the signal loss through the coax cable. And there are mainly four factors which will cause the signal loss through the coax cable. For example, radiation out of the cable due to imperfect shading, resistive losses in the cable conductors, and signal absorption in the dielectric of the cable, or the signal reflection due to the mismatch between the cable and the terminations, or along the cable due to non-uniform impedance. The D-plus glucose anhydrous food graded C6H12O6 with a molecular mass of 180.16 gram per mole was used in the experiment, and the experiment began with a 10 ml of distilled water, and each time the D-plus glucose anhydrous food grade increased by 0.2 gram and stirring until it was evenly mixed, and all measurement results were recorded and discussed. From the graph 4.1, it's observed that the resonant frequency of the design sensor uses FR4 substrate shift toward lower frequency when the concentration of glucose in the solution rises. Increasing the glucose concentration could be explained as an increase in the capacitive reactance due to increase in the dielectric constant of the sensor environment, and therefore the resonance moved to a lower frequency, and moreover, a trailable amplitude change in the particular resonance was observed in graph 4.1 because of the small difference in the loss tangent among the different glucose concentration samples. And according to the graph 4.2, it's observed that the frequency laceration for the glucose level changes at a respective resonance is 0.0035 GHz per 0.2 gram per 10 milliliter, and therefore the resonant frequency resulting from filling a specific concentration of glucose solution can be estimated using the linear regression model derived as the equation below. On the contrary, the unknown concentration of glucose in the tested sample can be predicted using the inverse model. Graph 4.3 is observed that the frequency response of the design sensor using the Rogers substrate has the same trend as the frequency response of the design sensor using the FR4 substrate, which is that the frequency shifts toward the lower when the concentration of a glucose solution rises. And according to the graph 1.4, it is observed that the frequency resolution for the glucose level change at the respective resonance is 0.004 GHz per 0.2 gram per 10 milliliter. And according to the graph 4.4, the resonant frequency resulting from filling a specific concentration of glucose solution can be estimated using the equation below. The resonant frequency resulting from filling a 10 ml Coca-Cola drinks were measured using the vector network analyzer and recorded as shown in the figures 4.12 and 4.13. And the resulting resonant frequency for the design sensor using the FR4 substrate is 2.037 GHz. With a resulting resonant frequency, the unknown concentration of glucose in the tested sample can be predicted using the inverse linear regression model as shown in the equation above. And based on the calculated result, the concentration of glucose in the tested sample for the design sensor using the FR4 substrate is 0.46 gram per 10 milliliter. Next, the resulting resonant frequency for the design sensor using the Rogers substrate is 1.427 GHz. With a resulting resonant frequency, the unknown concentration of glucose in the tested sample can be predicted using the equation above. And based on the calculated result, the concentration of glucose in the tested sample for the design sensor using the Rogers substrate is 0.45 gram per 10 milliliter. And based on the nutrition label of Coca-Cola drinks in the figures 4.14, the total sugar present in 100 ml of Coca-Cola drinks is 4.6 gram, and therefore it's clear that the total sugar present in 10 ml of Coca-Cola drinks is 0.46 gram. And by comparing the measure result in the table 4.4 with a nutrition label of Coca-Cola drinks, and it is observed that the design sensor using the FR4 substrate has a higher accuracy than the design sensor using the Rogers substrate. The design sensor using the FR4 substrate has a higher accuracy due to the fact that the sensor using the FR4 substrate has a higher sensitivity than the design sensor using the Roger substrate, as shown in the table 4.5. And the best achievable sensitivity for this project according to the table 4.5 was 1.7 kHz per milligram per deciliter, which is significantly beyond the best finding published in other literature, regardless of the shape and the volume of the sample under test. The resonant frequency resulting for filling a 10 ml Angela Sandy drinks were measured using the vector network analyzer and recorded as shown in the figures 4.15 and 4.16. And the resulting resonant frequency for the design sensor using the FR4 substrate is 2.03450 GHz. With a resulting resonant frequency, the unknown concentration of glucose in the test sample can be predicted using the equation above, and based on the calculated result, the concentration of glucose in the tested sample for the design sensor using the FR4 substrate is 0.6 gram per 10 milliliter. The resulting resonant frequency for the design sensor using the Roger substrate is 1.424 GHz. With a resulting resonant frequency, the unknown concentration of glucose in the tested sample can be predicted using the equation above. And based on the calculated result, the concentration of glucose in the tested sample for the design sensor using the Roger substrate is 0.6 gram per 10 milliliter. And based on the nutrition label of Angela Sandy in the figures 4.17, and the total sugar present in 100 milliliter of Angela Sandy is 6 gram, and therefore it's clear that the total sugar present in 10 milliliter of Angela Sandy drinks is 0.6 gram. And by comparing the measured results in the table 4.6 with the nutrition label of Angela Sandy, it's observed that the design sensor using the FR4 substrate has the same accuracy as the design sensor using the Roger substrate in this case. In a nutshell, all the objectives of this project were achieved, and based on the calculated percentage error, there is a good agreement between the calculated data and the HFSS simulation data. Besides, based on the calculated percentage error, there is a small difference between the calculated data and the actual PCB measurement data due to the signal lost through the coax cable. The resonant frequency resulting from filling a specific concentration of glucose solution can be predicted using the linear regression model. On the contrary, the unknown concentration of glucose in a tested sample can be estimated using the inverse model. The best achievable sensitivity for this project was 1.7 kHz per milligram per deciliter, which is significantly beyond the best finding published in other literature, regardless of the shape and the volume of sample under test. Based on the calculated percentage error, there is small difference between the calculated data and the actual PCB measurement data due to the signal lost through the coax cable, and therefore the current design can be further improved by using the height-graded coax cable that uses the lower resistance method for both wire and shading. Besides, the current design can be further improved by using a shorter length of coax cable, as the amount of ohmic loss is proportional to the length of the conductor. And these are the references I used for my presentation. Thank you.